My name is Antonio Coleman, and I would like to welcome you to my newest series where I will discuss various data structures and algorithms within the field of computer science. In today's installment, I will be discussing BST red-black trees. However, before we dive into red-black trees, I feel that it is very important to understand what BSTs are and what the acronym actually stands for. BST stands for binary search trees, which are defined as data structures that have both a unique key for each node, and also all nodes in the left of a subtree should contain values strictly less than the node's value, while all the nodes in the right subtree of a node contain values strictly greater than the node's value. Attached here I have a visual reference to binary search trees from the website Geeks for Geeks. Some real-world use cases for BSTs can include database indexing, search auto-completion, as well as spell checkers. Database systems, however, are the most common use of BSTs as they allow effective querying when indexing the tables, thus positively impacting efficiency. Additionally, BSTs can be helpful in auto-completion programs as well. This can be seen in how we type the letters within apps and get suggested the most common outcomes. Like, for example, if you typed APP, more than likely some common outcomes that you will receive would be apple, apples, or application, and this is done by traversing the BST. Moreover, in spell checkers especially, BSTs allow the system to simultaneously check to make sure that the word is first spelled correctly, and then secondly, also search the stored dictionary to help make the process seamless. Now, after knowing this new information, you may ask, well, where do BSTs go wrong or become ineffective due to common pitfalls? To this, I will answer that this can occur when used in large-scale applications, and this is due to the massive amounts of memory allocation and overhead needed to implement BSTs within bigger programs in comparison to the compact nature of red-black trees. Additionally, BSTs can become unideal on applications that require continuous iterations or modifications for a similar reason. However, in this example, BSTs are non-ideal due to the potential conflicts with balancing. This overlaps with the next portion about the advantages of red-black trees. Now that we have built a solid understanding of BSTs, we can discuss red-black trees. While standard BSTs are fundamental data structures within computer science, red-black trees address the most common concern within binary search trees: balancing. This is because red-black trees are a self-balanced binary search tree that uses a set of rules to maintain its balance. This is done to ensure logarithmic time complexity for the common operations such as insertion, deletion, as well as searching. Moreover, regardless of the initial shape of the tree, this process is done seamlessly. Attached, I have a good visualization of this, which can be referenced back to Geeks for Geeks as well. Lastly, these are my references. Thank you for watching the video.